very easy to directly represent decimal numbers. This is not a numbering system, it is a code. Y'all understand that? We say we do. But on the next test, I'm going to say convert this number from binary from decimal to binary. Somebody's going to write down BCD. I guarantee.
BCD is a representation of the
but it's not weighted.
No, what I'm saying is, if you asked me that, I would say that's not the same thing as BCD.
What?
The question you asked me.
No, what I'm saying is that going from one weighted number system over to another weighted number system. So when I say convert, I'm looking for my PowerPoint so I can bring up a slide. In fact, let me just bring up a blank PowerPoint. That'd be better. So if I was going to take a real easy one that I know in my head. If I was going to take the decimal number 100 and I was going to convert it to binary, what would be the first thing we would do? Well, I would start up and write a decimal equivalent of the powers of 2. 1, 2, 4, 8, 16, 32, 64, and I always go one past what I need, because that way I know I got enough digits in there. And I would say, okay, what's the biggest thing I can subtract from 100? Okay, so I'd put a 1 on 64, and I'd write 64 over here, and what do we end up with? Okay, so I'd bring 36, right? Can I subtract a 32? Okay. And then I would say 32. And what does that leave me? 4. And then I just go ahead and I can fill it in now. Okay, so that is true. So if I came over here and did this, 100 base 10 is equal to 1, 1, 0, 0, 1, 0, 0. That would be true. Now what we do on BCD is we use 4 binary bits. Now the problem we have is with 4 binary bits, how many numerical combinations can I represent with 4 binary bits? So I take 2 and I raise it to 4, and that gives me 16 combinations. So with 4 binary bits, this is weighted right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I don't run out of room, 13, 14, 15. There's 15 combinations, weighted. Those are weighted. These are 2 weighted numbers. What we do on BCD, some people call it the 1, 2, 4, 8 code, is I just look at each one of these digits and I use 4 binary bits to directly convert it. So this would be BCD right here. 1, 0, 0, and this is BCD. Now look at the difference between that number and that number right there. Are they equal? No. That on the top is a code. We're sacrificing 6 digits. So in BCD, these are the only legal combinations in BCD. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's BCD. What did I just sacrifice for BCD? I sacrificed all those. With 4 bits of binary, I can do 16 combinations, but what I'm doing is I'm throwing away 6 of them. This is not a weighted number system, it is a code. But what I can do in BCD is I can write down any number like that, and I can come down here and you have to use 3 bits. You have to use 4 bits because it's a code. So that is not weighted, that is part of the code. So you can't drop any zeros, right? Legally, you can't drop any zeros. 6, 3, 9, B, C, D Is this weighted? No, it's a watt. It's a code, but I guarantee somebody in this class, when I say go from decimal to binary, they'll give me a BCD answer.
Each number is its own 4-bit.
Each number is its own 4-bit. And so it don't go 1, 2, 4, it goes 1, 2, it goes, and 1, 2, 8. It goes 1, 2, 4, 8. It goes 1, 2, 4, 8. It don't, and a lot of people call it the 1, 2, 4, 8 code. They don't call it BCD. So it don't go 1, 2, 4, 8, 16, 32. It goes 1, 2, 4, 8, 1, 2, 4, 8. And every group is what? Is one decimal. It directly represents one decimal digit. Now this guy has been around so long because you can see how neat it is. We have in digital, we have counters that count in BCD. They electronically, it's real neat, actually drop 6 of the counts. I can show you the circuit. We could design it, but you might see it if you take digital. But we have BCD counters, which is really neat. And why do we need those? Because our displays, a lot of times on our display, we use what we call a 7-segment display, which we'll look at later. And they call it a segment 7. And y'all see these guys all the time. You just don't realize it. And I'm drawing them attenuated. And then we just turn on, we call them segments. We turn on different segments to display different letters. Well, the only thing we can really do with this thing is the decimal numbering system. So we have BCD counters, we have special integrated circuits that'll drive these things. So my BCD counter's down here counting, and this display up here is going 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. It's really neat. So BCD has been around for years, but it is not weighted. It's a what? Code. It's a code. So we have BCD counters. Our PLC can later on when we get into if you take the advanced PLC, we have commands where we can convert a binary code over to BCD code, so we can send it to these displays, so it'll display real decimal numbers on them, because we don't understand 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? So, or even binary. Binary is even harder.
When we're done with all these labs, do you have a box for?
Yeah, well, it's actually down in the lab. So when we go in the lab down there, that's what we'll turn. That's what we'll turn. It's Tuesday.
But if we got them done.
Got you upset, did you? Hair was going. So there's a drawer down there. It's labeled, right now it's labeled ILT 196, because that's the class I usually teach. So in chapter 6, how far did we get? Oh, all through the rules, right? And we talked a little bit about them. The rules are okay, but the way yeah, the rules for ladder logic, for relay logic is in 5, and the rules for PLCs are in 6. And they're very, 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 very similar, right? Are you okay on what we call a scan? What's a scan? So what does the PLC do when it starts running?
Okay.
Yeah, it starts scanning the ladder. Starts over here and does what? Scans across, and then does what? Scans across, scans across. So it starts in the upper left-hand corner. Input first, output last, and then it ends up down at the very bottom of your ladder diagram in the lower right hand corner. And then when we look at, if you take advanced PLC, we'll look, every one of these instructions requires so much time for the PLC. So the larger your ladder diagram is, the longer the scan time. That makes sense. Now, what we're going to learn in advanced PLCs, and this book is basically touching on it, is that most large PLC programs are split into separate little modules that we refer to as subroutines.
So what?
Subroutine. So what you do is you have one main module, and what this thing does is call these other little programs out. Now, what this does is it means I'm over here in my main module, I'm scanning that. But when I go to a subroutine, then I'm only scanning that, right? Understand? So it helps, instead of going through the whole, instead of having a program that's, 1,000 runs of code, you might have, 100 programs that's got 10 lines of code. And you only call those modules when you do what? When you need them. That makes sense? And we call that structured programming. We'll show it. And the book talks on it just a little bit when it starts talking about the layout of the display. So we've already looked at this. We looked at this, how to set this. Y'all know how to set up a run, right? Y'all know how to enter these instructions. Are we okay? Everybody okay on that? Any problems on there?
Can you go over again?
Well, what we'll do is I'll bring it up on Logic Pro. Logic Pro is a little different, but it's good enough to do what we're going to do. And we'll talk about the problem. The first thing we'll come up here and we'll type in, when we hit new up here, and this is the same. Of course, if I'm in program mode, so what I need to do, I need to go out of program mode, and then we're going to go offline. And then we're going to come up here and we're going to go new. And then the first thing we need to do is what? Yeah, select the processor. It depends on if you select a modular processor. If you're on one of the 504s down there, then you're about to do two things. You're about to select the processor, and then you're going to have to configure the I/O, right? Y'all understand that? If you're on a PLC, all you got to do is what? Select the processor. Everybody okay? So the 1000s that so down there when you get into the lab, we got two types down there. We got the 504s, and then we got the 1000. But as far as the lab goes, the only difference that it's going to make is this section right here. Then after that, everything's the same, except for addressing.
The differences I see are the 64, 32, 16, 24, A.
Yeah, so a lot of it deals with the type of memory you got.
So if we're working on the 504, which there's.
When you open that little door right there. You open that little door right there, and you look and see what the model number of your PLC is. Now on your 1000s, the model number is going to be on the side, right? Y'all understand that? We don't have a door. And what's nice about the modular PLCs is the CPU does not take up a slot. The CPU does not have an address. So did I say that right? On the fixed PLC, I think I said modular. So on the fixed PLCs, the CPU has no address. So it does not occupy a slot. And also on the fixed PLCs, especially on the MicroLogics, your I/O ports start at 0. Your inputs ports are considered slot 0, and your output ports are considered slot 0 because there's no slots, right? Does that make sense? Now on your hybrid PLCs, you come in here and you'll slap something on the side, which are these 1000s that we have. These are fixed, pure bred fixed PLCs. You don't hardly find these anymore. So they come out with what I call a hybrid PLC, which you buy it. It's got the CPU. It gives you so many inputs. It gives you so many outputs. And then it's got this little thing on the side where you can snap. So we don't have a backplane, literally a backplane anymore. And we don't have a chassis anymore. What we have is we have some type of rail, which is that DIN rail I passed around, and everything snaps onto that. Right? Now when you do that, now you're going to have to specify a slot number, right? Does that make sense? And of course, a lot of times that is totally configurable too. So we'll look at that. So this one, Logic Pro, if you use this is not exactly true because they're not going to make you configure I/O, I don't think. We'll have to look. But what I'm going to do now, just to save time, is I'm going to come down here and
What determines which one you choose?
which one you got,
Oh.
right? You understand? So if you're set down in a computer and this is attached to it, then this is the 504, this is the modular PLC. So what you're going to do is open up the door that's on the CPU. You're going to look at that model number, right? You understand? And when you list the list, you'll find that model number. And then what you're going to have to do, you'll have to configure the I/O, right? You understand? And where's that information going to be at? It's going to be on the door down at the bottom. It's going to have the model number of that input and that output module. And you'll have to configure those two, right? Everybody okay? A fixed PLC, though, all you'll do is come down here and find it. I think I went by it. Yeah. And then you're through. Are we okay? Let's see. And now you're ready. So what would you do? So here's all your instructions up here. User, these are your most often used instructions. If you go over to bit, they're basically almost the same thing. These are the true bit instructions. Normally we use, mostly in this class, we'll move these. So the only two we're going to use is this guy and this guy right here. So that's the only time we have time covering this class is basic instructions, the bit instructions, and then timers and counters. And we just basically touch on counters and timers. And then if you take the advanced PLC, we'll get into more about timers and counters, how you can do some neat stuff with timers and counters. And then what do? Well, first thing you got to do is what? You got to insert a rung, right? You understand that?
Can you
So-
not, if you only have one circuit, can you not use just the one run?
You can't use this. This is not a rung. This is the end. The end is the last rung in you cannot put anything in this thing.
I knew that the icon in, but I didn't realize it was the
Yeah,
entire
this is
circuit.
the end. Yeah, automatically when you create a program on the Allen Bradley PLC, it puts the end instruction out there. You can't do anything with it. So if you look at your whole instruction palette, you're not going to see an end instruction. You okay? So I'd highlight here, then I would insert my first rung, and now it's ready for me to start putting stuff in, right? Are you okay? If you know you're going to do 4 rungs, you can come up here and you could, on that, this won't let me do it, but yeah, it will. You could go ahead and put your 4 rungs up here. If you wanted to, it's up to you, you know, and then fill them in as you go along. So you can put as many rungs up there as you need. Let me go. Let's see what Logic Pro does if I choose one of the modular PLCs. So I'm going to go over here and say new. By the way, on Allen Bradley, so this is a simulation. This is a simulation. On the Allen Bradley PLC, if you go up and start a new program, it's going to ask you, do you want to save the program that you got? Logic Pro don't do that. If you exit out of the RS Logic software and you got a program running, it's going to ask you, do you want to save it, right? You understand, like most Windows application does. Logic Pro does not ask you that. So if you do Logic Pro and you exit and you don't save, what's going to happen? Yeah, you lose it. So it'll come up and say, are you sure you want to exit, but it don't give you an option. So let's see what it does. I'm going to come up here and do a new one, and we'll use one of the 504s down here. They don't have a 50, yeah, they do. And then we'll go back to the project tree. I think we can close this out. And then, yeah, so notice, oh, there we go. So it does. But what it did for us is that, I don't know if it lets you select it. What it does, it don't let you select it, it automatically locks. So it chooses for you. Now, RS Logics is not gonna do that, right? You understand that? Notice it don't give me the ability to even come up here. Maybe, let's see if it does. So we got it on input. Let me double click and see if it, good, no. Okay. And like we said, this is a simulation. This is not true. And what it's done, when you load yours up in RS Logic Pro, I don't think it's going to have all these other ladders available to you. But the MicroLogic 1000 will. I have a tendency to go right past them. So what figure is this? So everybody okay on the scan, right? Now what I want you to do, if you don't have a textbook, you need to get with somebody around with it. Let's look at all this stuff over here in the project tree and talk about that. So this is on page 116. So what they're doing is explaining everything that's over here in our project tree for us. And by the way, this is RS Logic right here. This is the real thing. So the first thing we start off with is our output register. Depending on the PLC, the RS Logic 500 series of this programming software that we got supports up to 256 of these registers. Now that doesn't mean how many you're going to have, because it's going to depend on how much memory you have in your PLC. But think about that. We got 256 of these things, 0 through FL. And each one of them have 16 bits. That's a lot of output, right? 16 times 256. Odds are you're not going to run into that, but that's the limit of RS, of the Logic Pro, of RS Logic's 500. So just about all these registers are limited to 256, especially, and then it all depends exactly how many you got, depends on how much memory comes in your CPU. I'm sorry, in your PLC. So we have inputs and outputs. Are y'all okay there? And we can look at these registers. All you have to do is come over here and just click on them. I'm sorry, double click on them. And then this shows you what's going on here, right? You understand? Okay. So this is our input registers. And then we have what? Then we have outputs. Then we have what? Inputs. Everybody okay? Yes or no? Okay. Then we have the status registers, which you can't do anything with. That's actually controlled by, I'm sorry. You're going to have, let's go back up here. I think it starts up here. Yeah. So here's our program file. So we have system 0, system 1. You can't do anything with those. Those are controlled by the PLC. And then we have what Alan Bradley refers to as ladder 2. This is ladder 2 right here. So ladder 2 is what you're going to be playing around with today. I mean, not today. Just hoping take the advanced PLC class, we'll get into some other ladders when you start playing around with multiple codes. Now, what you notice though, is I don't think the book talks about this, but notice in the main menu it says ladder 2. So when you open up your program and create a new program, it's going to be called ladder 2. But guess what you can do? You can name it. So you got two places you can do this. You can come up here and right click it on the project tree and choose what? Rename. Or you can come down here and click on the tab and rename it. Now it's still called ladder 2, so you look in your project tree, it's still ladder 2, but now it has a name. And of course this will mean it makes a little more sense, right? When you start, especially later on, you start making multiple subroutines down. Then ladder 3, ladder 4, ladder 5. Now what happens on your PLC, so this is my main program, but you look on the 1000, ladder 3, ladder 4, and ladder 5 are dedicated. So that means you cannot put a program in those three, you cannot put a program or a subroutine in those three ladders. Those are dedicated. One of them's dedicated to user faults, ladder 4 is dedicated to high-speed counters, and then ladder 5 is dedicated to so these are handled what they call interrupts. And we're not going to get into interrupts in this class. We'll get into on a fixed PLC. When you look at these ladders, some of them are already going to be dedicated, right? You understand? So if I was going to create more ladders in this program, I'd have to do it from 6 to 15. This is all that the 1000 allows. Are you okay? Everybody okay? Then we get down to the data files. So these are the data files that are covered in 116. So our data files, we have our output data files. This is going to hold, this is where all our data is stored, going to our outputs, our inputs. This is where all those bits are stored when the PLC reads up the input. Status, we use this for what we have in microprocessors is we have things that happen that we need to know when they happen. It might not necessarily be a fatal error, but we need to know when it happens. So we've got these registers in there, and I add two numbers together, and it comes up bigger than the register will hold. Well, is that an error? Maybe not, but we need to know about it. So we have what we call these status registers that we use to tell us when things happen. Does that make sense? So what we can do with our program later on, if you take advanced PLCs, is know how to utilize those registers. So if you do have an overflow, then you can do something about it, right? Your program can do something about it. We call those status registers. So these are used by a lot of instructions. They're used by sequencer instructions. They're used by bit manipulation instructions, how we move things around. And right now, we're not going to be able to use this. We are going to use the B3 register. What does it say the B3 register is used for? But what's it used for? Internal contacts and relays, right? You understand. And we also can use it for just about anything. We can put data in there. We can just use it as temporary storage when we want to do something. So if I want to input a group of switches. So right now, what y'all are going to learn is I can bring in one input at a time. Later on in advanced PLCs, we can bring in a whole word of switches. But we got to be able to put those somewhere when we bring them in, right? Instead of using the program. So this is where we're going to use these B3s and B10s. This PLC does not support a B10. Some of your PLCs supports a B3 and a B10, which is basically the same thing. It's just another bit register. So instead of having 256, now you got what? You got 512 that you can do with. Timers. This is going to hold information about our timers. So when we get into timers, everything we're going to do in there is going to be in there. Counters, when we get into counters, all the information about our counters are going to be in these things. And then the control register. This is where we're going to be able to control, specify some control for our process or for our program. Integers, y'all know what an integer is?
Real number or the?
Well, it's a number without a fraction. It's a number without, it's a whole number. An integer is a number without a fraction. One register that they don't talk about, which you need to make a little note, it's not up here, is the F8 register. F8 is for floating point number. What do I mean by floating point number? Floating point number is a number where the decimal point can move within the number. We use floating point numbers all the time. So a cash register uses what we call fixed point. So a cash register, your decimal point would always be right there, no matter what you enter. So if you ever worked with a cash register, you start entering numbers, and it'll start on the right, left-hand side, or even your microwave uses fixed point. So your microwave, you got your decimal point right there, right? You start typing 1 minute, it starts up on the left, and then the more digits you move, but what does the decimal point do? Stays. A floating point would be a floating point. So a floating point number, you know, you can say what? You can say 0.356, or you can say 122, 0.9864732, and it goes on and on. So a floating point number is where your decimal point has the ability to move within the number. Also, floating point supports scientific notation. And what scientific notation?
One number behind.
Well, this is when we start doing exponents.
Three numbers.
No, that's engineering notation. Engineering notation is a form of scientific notation that engineers use. So instead of jumping in one digit at a time, which scientific notation does, engineering notation always moves in groups of 3, no matter what. Well, no, scientific is anyway. Scientific is so I could have 123.92, right? You understand? Times 10, it's still times 10 to the minus 1. We don't have that. We don't have that in engineering notation. The best we would do would be minus 3. Or I could have 3.62 times 10 to the 18. Let's don't do it. Let's say times 10 to the, well, that's that group of 3. But we could say 13. Well, this is scientific notation. Well, that's scientific notation. So engineering notation is a form of scientific notation. It's just that moving. So in scientific notation, we can move one decimal point at a time. The powers of 10 raised to it could be negative or positive. So this is what your calculator uses. This is exactly what your calculator uses. So when you exceed the range of your scientific calculator, it automatically jumps into what? Not engineering, scientific. It only goes into engineering notation if you tell it to. Yeah. So by default, if you exceed the range. So your calculator automatically by default uses floating point, right? And it uses a scientific notation. Now you can tell your calculator to do fixed point. So if you see a key on there called fixed, then you can come up here and you can hit that and make it do 2 decimal points, 3 decimal points, and they'll always do that. Which is usually what I do. I used to do that when I did grades in a spreadsheet. So I'd use fixed point math, and I'll always round to 2 decimal points. Well, if you round to 2, that's going to be fixed point, right? Are we okay? So the ones we're going to use, here you'll be able to actually monitor your inputs. So here's the inputs on this PLC. So I press this button, it goes to what? Can y'all see it? 1, bit 0. Here's the next one right beside it. Now here's the next one right beside it. Here's the next one right beside it. Here's the next one right beside it. Here's this guy. These are selector switches. So even if I didn't know where these bits were, because you get out there in a system and it crashes and you lose everything, right? You understand? And you say, well, I don't even remember, somebody didn't document anything, which should be shot for anyway, right? You go out there and say, man, I don't know anything. So we've got PLCs in here before that just, and we try to figure out, well, we just bring up this thing and start switching these buttons, and we say, okay, this port is assigned to this one, this is assigned to this one, this is assigned to this one. And then we can force outputs too. We'll talk about it a little bit. Are we okay? So there's our timers, and now of course I added F8. Everybody okay on F8? So what's F8? Floating point. And so what you do when you use these registers, you start off with that same, so this is B3. So if on timers, we're going to start off with what? All your timers are going to start off D4, right? All your counters are going to start off C5, right? You understand? And then you'll assign a number to it, just like you do an input port. So this timer right here, this is T4 0, right? You understand? Your second timer would be called what? T4 1, right? You can't assign a bit in the time. If this was a counter, it would be what? C5 0, C5 1, C5 2. But you're still, this is not, so here, this is not identifying the slot number, after the colon. It's identifying which timer you're going to do, your address. And when you do that, it's going to assign memory. Every time you put a timer in there, it's going to assign a memories down inside this T4, the T4 memory data file. Okay? That makes sense? Well, where's my PowerPoint at? We talked about this. Everybody okay there? And this is kind of misleading too. I don't know where this is in the book. Like I said, these are not my PowerPoints. This is only true in a slot in a modular PLC, right? So this is not even true for our 504s that we got. So what we got, of course, slot 0 is on modular PLC. Slot 0 is going to be the PLC. It's going to be the PLC, right? Slot 1, slot 2, what's going to be there? What do you think of? In fact, our 504 uses a syncing input module and a source and output module. So those are DC modules. So this is not even true for our PLC. Our 1000s that we use, and y'all got to be careful with this thing, guys. See if it focuses. Come on, focus. Boy, it was beautiful while ago. It uses DC inputs, uses relay outputs, and it's powered by AC. So this is where you got to be real careful when you open this door right here. Here's the power. Y'all don't see the power plug, but it comes in and comes right into this slot right here that says line 1, line 2. That's 120 volts AC right there. Y'all understand that? And these are relay outputs. So I don't know if y'all can see what they've done. So it's relay outputs. On a relay output, you can specify what type of voltage and current you need. So a relay output, that's one of the big advantages. You can use AC, you can use DC, you can have syncing or sourcing. It's up to you. So you notice what they do. Here's the hot side. And these are jumping down to all the columns on all these outputs. But what do you think's on all these thing outputs right here? 120 volts. What do y'all need to make sure you do? Leave that door closed, right? Y'all have no business in there. In fact, it's got this big old warning label right here.
What, 24 volt DC input?
Yeah, 24 volt DC input. It has its own built-in power supply. What's neat about Allen, well, I wish this thing would focus. Good gracious. Come on, focus. What this does is these are configurable inputs. So you can't see it, but that's DC common, that's DC common. So what you do is you can set these up as either syncing or sourcing inputs, whatever you use as a common, but it's DC. What they're doing is they're taking the minus, so this is minus DC right here. I'm pointing to it on my computer. So this is plus DC, this is minus DC, and they've got this jump to the common on this one, and then they've got it jump to the common on that one. So that means that they're using, the PLC is set up to sync. So that means all my switches are set up to source. You can see what they did. Now, a lot of your fixed PLCs, you don't get this option, but Allen Bradley likes to do that. So that way you can, but it goes in groups, so you can't set them all up for syncing. You can't set them up all for sourcing. So these groups right here, this can be set up to either sync or source, and this group right here can be set up to sync or source. But you can't do all of them. You don't have individual. Now, out here on our outputs, we have the ability to set up each one of them. And then these are the LEDs that come on when you activate an output. So this guy's got 6 outputs, and it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inputs. So when I press an input, this has got a program in it, by the way. So see, when we press these inputs, and this is what's nice about a PLC, it gives you another tool for troubleshooting without pulling out your meter. So with motor control, to see if we were getting power to these guys, we'd have to get a meter out and read it. On here, if you press that button and that light turns, then you know the wiring all the way from your from your input all the way to your PLC is good. So you're through right there. And then I'll show you the monitor. So guys, keep the watt closed. If you get on one of these, keep the watt closed. Door closed. But up here it's okay, because this is 24 volts DC. You can touch this. Just don't put your tongue down there. Out of US Steel, we had these batteries. One of them was rated at I forgot what it was. It's like 6 volts, and the other one's rated like 60 volts, and they looked almost identical. And we had a guy in our shop. He'd touch his finger and put it on the bottom of the battery, touch it against his tongue. I'll do that with 9-volt batteries. Huh? Yeah, 9 volts. But what we did is we snuck that 60-volt battery in on it. He said a few choice words. Let us know he didn't appreciate it. And I don't blame him. That was thing. Okay, so this one, y'all see this figure right here. So what we're doing is they're taking a line they looks like they're going to take did they give us the line diagram for this? What page is this on? What figure is this? That 119, y'all look at 119. This one's pretty straightforward, and we're going to start talking about where the book's got problems at. So this would be a fairly simple.
That's 645 program scan. It's got 1, 2, 3, 15.
Yeah, 113 is correct.
One what? Now this is supposed to be the connection for the circuits shown on 113, right? Got a start, stop, got a main contactor in it. Are we okay? So this is the circuit they're showing us right here. Now this is a normally closed stop button, right? Now why do we like to use normally closed? For stop buttons. Yeah, well let's is everybody okay with examine if closed and examine if open? We're going to have to, because even the guy in the book's got a problem with Bit 3, so bit 3, what we're gonna do, bit 3 register. It says we can use for shift instructions, sequencer instructions, we haven't got there yet, we're not gonna get there in this class. Some of the things that he talked about, we're not gonna get to in this class. Most often what we'll use it for is what we call internal relay instructions. That's what we're talking about. In a true motor control circuit, probably 80 to 90% are not driving power. They're not a power circuit. It's just a control circuit. And what we find out is that we can program every bit of the control circuit into the PLC. And if it does not require an output, then we don't need to sacrifice one of our outputs. This guy right here has only got 6. And I use something for a relay that never needs a contact outside my program. I sacrifice one of my output ports. This instruction, so this is pretty good. This is okay. This is done with our Logic Pro. Logic Pro, your symbols, they use orange. In RS Logic, they'll use green, right? 90%. But notice what he's using. He's using B3. He's not using an output port. He's using B3. So B3 if you use the B3 register, it does not use one of your output ports. Y'all understand that? And these are contacts for relay contacts that are never leave your control diagram. So every one he's using here is using the B3 bit. B30, and we address it the same way, but instead of starting out O, right, colon, we start out B3. Then we put a colon, and then we put 0, because we don't have more than one B3 register. 0, and then you put the bit within the B3 register. Everybody okay?
So they're all going to be B30?
Yes. No matter what. But you got 256 words, 16 bits per word, so you got a lot of it. But you use it just like you do this output enable, this output energize, but here the output is not physically an output port, right? Everybody understand that? Yes or no? And if you have the B10, you can also use it. I don't think our 504s has a B10. I'll look and see. I'm not hooked up to that now. I know the 1000 don't have a B10. So these are some problems. So let's look. So look at this diagram right here and tell me, this is motor controls. So this is a nice motor control diagram. I've modified it some. I don't know if this is 626. I've done it according to what it looks like. It looks like this guy is PLC. And he never had a ton of experience with wiring electrical controls. He's been programming PLCs. And that's what he looks like to me. Okay. Fortunately, I've done both of them. So what are these over here?
Those would be
Line numbers. They're not rung numbers. In motor controls, we don't deal with rungs.
line numbers.
In motor controls, we use lines. Okay. We don't number the rungs. We number the lines. In PLCs, we number the rungs. Right? You understand?
Oh.
We still call them a rung, but in any line that runs horizontal, it's a what? It's a number. These are cross-reference numbers, and what do they show you?
Which line?
Contains the contacts, right? Okay. Everybody okay? Yes or no? So then he comes up and he says, okay, this is the way we're going to wire it up. This is the legal way to wire it up. He comes up here and uses the normally closed. That's a symbol for normally closed push button, which is legal, right? Why do we want normally closed for a stop? So it'll break, right? So it'll stop if the wire breaks, right? You understand? He uses a normally open for a start, and he uses a normally open for a jog. So we know what jog is now, right? So jog means I have the ability somehow to not make that thing latch in. I have the ability to. Then this is a symbol for a motor. or it could be the symbol for a, very seldom does the PLC run a motor. Probably 99.99% of the time it brings in a relay, and the relay runs the motor. Now to run a motor you need a relay. A solenoid means we're gonna push something, right?
You know, can't some solenoids be kind of same thing as relay?
Well, no, you're exactly right, but you're also wrong. A solenoid has no contacts on it. But as soon as we put contacts on the end of that big piece of metal, it's no longer called a solenoid. It's called a relay. So you're exactly right. But when we use the term solenoid, it's just a linear actuator. But a relay is a combination of a what? Solenoid and a switch. That's exactly right. Yeah. And so a solenoid has a different symbol, right? It's got that up-shaped symbol, kind of like a cut-off resistor, but it only has one up and one down.
Did you say PLCs don't use motors?
No, I said PLCs very seldom directly run a motor.
Run a motor.
PLCs will pick up a relay,
Right.
and the relay will run the motor.
Why is it there without a contact relay now?
Because this is the guy the way he drew it. We can run a motor, but it's going to be like a little tiny, small, little tiny motor, like the one that spins your microwave oven little trays. You got that little motor under there. It's a little old tiny motor, right? You understand? So it might run that. It might run these little motors over here that we run. We run them directly off the PLC. These are only 24 volt. Good gracious, these things probably pull 2 milliamps. They're not even loaded. Well, we can run that. Generically, the contacts on most PLC, or the outputs on most PLCs are rated just around 2 amps. But that's just generically, right? You understand? What you need to do is, if you want to find out how much current's available on those outputs, you need to look up the model number, and you need to find that online. That makes sense? AC will not be labeled plus, so that's another problem he had. If it's AC, it's going to be labeled what? It's going to be labeled AC.
AC.
Yeah. There's no such thing as plus AC. There's no such thing as minus AC. Normally, we don't, on a PLC, we don't use the term common unless I have the ability to configure what common is. So if it's a sourcing output, it's going to be labeled plus, right? You understand? Right? You understand? By the way, Siemens uses L plus for the plus DC, and they use M for minus. And why they do that, I don't know. So according to this, it looks like the inputs are syncing, the input is syncing and the devices are sourcing because it's labeled plus. AC, there's no such thing as syncing sourcing. AC will not be labeled with a sign, but with AC. Example, 120 volts AC. The term common is only used on DC modules if it can be changed from plus to minus by the end user. Does that make sense? Now, what does he have hooked up to port 0? Input 0. No. He has a normally closed push button for stop. That's exactly what he needs to do. What's wrong? What's wrong? This would never work.
Start and center.
Let's start with fine. Everything's fine. The problem is that sucker right there. He's using the examine if open. Y'all understand? And this gets, and I asked y'all, did y'all understand? Okay, so what?
I mean, like, I thought you could use either one you wanted.
You can. The problem is you can use either one of you won't. But but if I put this guy, I've got to use a normally open for my stop button. Because it's examined if it's open. So if it's closed, it's going to be false. And this is the problem, guys. This is one of the hardest things for us to understand. Now, most of the time we can get by with it. But let me bring up Logic Pro.
Right now,
And what's it? What figure? Huh? Yeah, it's true if it's open, but the switch is.
Isn't that what that was? Normal closed switch?
No, let me show y'all. Let me do this. Is this Logic Pro? So what I'm gonna do is I'm gonna open this figure. What figure is this?
I'm not sure.
Figure 628. Okay, so here it is right here. Right? You understand? Everybody okay? And this gives, I'm going to change this right now. So I'm going to come up here, I'm going to download, and I'm using a normally open push button. I'm using a normally closed push button for my stop button. That's what I'm supposed to be using, right? Y'all understand? So I'm going to come up here and I'm going to download this to my PLC.
That is what that symbol stands for, right?
No, that symbol stands for,
Contacted the slash through it?
that's what it stands for on motor controls. In PLC it says examine if open. This is an examine if open instruction. Y'all understand?
That's what you want.
No.
One hour and it's
But we already know it's normally.
No, look. Now here's 0 right here. What do I have on my 0? I've got a normally closed push button. Okay. So what I'm going to do is I'm going to come up here and I'm going to go online and I'm going to run this thing.
Why can I not represent a normally closed push button with an examine if open?
Because it's true when it's open. So if it's closed, it's false.
So it's just somebody just put the wrong thing. They really didn't want that push button. They just put the wrong examine. They should have put examine.
No, this is the guy. It's not somebody. It's the guy that wrote the book.
Yeah. But
Okay, but look, guys. It's supposed to be normally closed. I'm using a normally closed push button. It's supposed to be normally closed, and the rung is false.
Yeah.
Because it's true if it's open. So if I change this over here to a normally open push button, now it's true. It's true if it's open. We don't want a stop button to be true when it's open. We want a stop button to be true when it's closed. So I'm using a normally open push button for a stop button, input 1, input 0, and it says it's true. Right? Y'all understand? Yes or no? So that's what we need to learn. We want to make it true if it's closed, right? You understand? Yes or no? This is one of the hardest things to teach. So I'm going to change this over here to an examine if closed. Okay. Now it's false because my switch is what? Okay. So it's false. My switch is open. Examine if open. My switch is, examine if closed. My switch is open. I'm using the examine if closed. My switch is open. Let's say I want to make it true. Then what I'm going to come over here and I'm going to use a what? A normally closed push button. Now it's true. And this is what gets people in motor controls totally confused because they get that dang thing with an arrow through it. They say, well, that's a normally closed push button. It is in motor controls. In PLCs, it's an examine if open. So this is an examine if closed instruction. So look, it's true now. But what else is it waiting for? Now it's waiting for input 1 right here. Right?
You can't operate a system with it open, so does it want to know whether or not it's open so you won't run the system? You want to know whether or not
It's a stop button. It's a stop button. Right? You understand? It's a stop button. And we got 2 instructions. We got one that says it's true if it's closed, and we got one that says it's true if it's open. This right here is an examine if closed. So that means if it's open, it's false. Right? You understand? So the problem is people see that line through there and they think normally closed contacts and they want to say examine if closed, but that's not true. So what we're saying is this right here is true when it's what? Closed. So I'm using a normally closed.
Coincide with that.
That over there, that's motor controls. This is not PLCs, and that's the problem we have with people is take motor controls, because when we need a normally closed contact, we use a normally closed contact. Right? You
The way
understand?
I was gonna kind of show it, like with the light on, like if the switch is that normal, that push stop button has a light, signifies when the circuit is on and it's closed. It's kind of like, that's the recognition of it being closed. And then when you open it, it's false. It's true with the light on.
Yeah, and what happens? I don't. If I come over here and look, what I come over here and if I look at my I/O, oops, and I look at my inputs. So we're saying examine if closed. So what happens when I press this button? Let's see if I can bring it back up. So when this button opens, that goes to a 0. So what the examine and close and examine and open means, it says, okay, if I use an examine if closed, if this is a 1, it's true. If I use an examine if open, if this is a 1, it's false. Y'all understand that? And that's what you got to understand. That double bar like that is an examine if closed. No, this is an examine if closed.
And that's why it's the first bit.
If it's got the line through it, huh?
What? That's the 0 bit number in the line. You have to have that to be true before you can see it.
Yeah, because this 0 right here. You can be anything. It's just that when I look at my memory, this is the 0 bit for what? For module 1. Right? And this is what happens, and this guy right here. So what he does, if you look at figure 627, he's using a normally closed push button, and then he's using an examine if open instruction. Y'all see that? Yes or no? Go ahead, sir.
No.
Huh?
I'm getting aggravated because I'm like right on the cusp.
But look at it. So this is a what instruction? Examine and close. Is it true? Is this switch closed? Okay, so it's true. Right, you understand?
So there's a 1 up there.
If I come up here and change this over to that guy right there, that's an examine if open. You understand?
And then under run, it's 0 now. It's false.
Yeah, it's false. But if I come over here and change this over, let me take it to program. And I use the symbol for a normally closed contact, and it's got XIO out there, which means what? Yeah. And then I put it to run. Now the dang thing's true. But I'm using a normally open contact for a push button because it's examine if open. It's true when it's open. If I'm going to use a normally closed push button, right, then I'm going to have to use a what? Yeah. And what happens when you get to your sensors, what does your sensors give you? Well, that's what you got to understand, because that will determine which type of contact you use in your PLC. Now, when we use relay contacts are exactly what they say they are, right? You understand. But when I use these input ports, that's when it starts getting confusing. And this is one of the most confusing things that we have to teach, is that examine if open and examine if closed. And people don't understand why we have to use an examine if closed if we want to use and we do this all the time. So this guy right here has no normally open push button, normally closed push buttons on it. But we do have this switch right here. So if we want to simulate a true stop button, then we'll use this switch right here. Right, you understand?
Since it's a switch, would you put it as a switch?
No,
or would you keep it as a
we're
button?
simulating, right? You understand? It's just that this guy here gives us no option. That guy right there gives us no option either. So this PLC over here, the only thing we've got is normally open switches. So that means if I hooked up a motor to this thing and I use my PLC as a stop button, then I've got problems, right? You understand? Unless I come up here and take this, if I simulate a normally closed push button, I can push that up like that, right? That makes sense. And now it's simulating what I would run into in real life.
Let me ask you this, with that space that shows you that it is a push button that is normally open, is that to say that when it pushes, when it's making contact, right? And that is when your circuit is complete.
That's when it's complete over there.
Right.
That's
right.
when it's complete over there.
In real life. Okay.
When that circuit is complete, you get a 1 in the data. You get a 1 in that data bit. When that circuit is broken, you get a 0 in that data bit. So an examining closed looks for it to be a 1, and examine if open looks for it to be a 0. Y'all understand what I'm saying? So if I come up here and look at my look at the actual inputs. So that now here's this switch right here. Here's this bit right here. The switch is open. It shows me a what? It shows me a 0. No, it shows me a 0. When the switch is closed, it gives me a 1. Now what your examine if open and examine if closed does here is that it interprets it different. So your examine if closed, if that bit is a 1, it says it's true. But if you examine if open, if that bit is a 1, it says it's false. So it don't make any difference what I do out here. If I change this to a normally closed push button, then that bit right there is always a 1. Right? You understand? So if I say examine if closed, if it's a 1, it's true. If I use an examine if open, if it's a 1, it's what? False. And it only really comes into play on your inputs. Once you get into these relays, once you put these normally closed and normally closed contacts from a relay down in there, if the relay is energized, then the normally closed open. If the relay is de-energized, then the normally closed close. Right? You understand that? This only comes into play when you hook things up to this dang what? Input port. And I don't know how else to teach it. And it only really comes into play. So we have some PLCs out there. And what's nice about using examine if closed is that examine if closed is you can use normally open devices for everything. So you can use normally open devices to simulate a normally closed switch. You can use your normally open switch to simulate anything, right? You understand that. But the problem is when you get to this dang stop button, that stop button has got to be a what? It's got to be a normally closed. If it's not a normally closed, then what happens if you break a wire? Yeah, you got to have, according to OSHA, you got to have a way to stop a motor. You got to have a way to stop a motor. So I don't know how else to teach it. So this guy right here shows it right. I mean, he comes over and he says, "Okay, I'm gonna come over here." And I don't know how the other teachers got by with it. When he draws it over here, when he puts how he hooks up his PLC, what did he put on his stop? He put a normally closed push button. Then when he got over here and he drew his ladder, he used an examine if open instruction.
That's the 0 at the bottom, right? Or part of it.
No, that's the address. That's the address. That's input 0, bit 0. This is, now what Allen Bradley does, RS Logics don't do this, but what Allen Bradley does, it comes up here and puts this, then it puts the word number, and then it puts the bit up under that. So this is input, word 0, right? Or port 0, bit 0. So this right here means nothing, that's the address. You can see every one of them do the same thing over here when they're using all these bit files.
You know,
Okay.
how when the motor is started and that affects the control relay, does it automatically closes?
You gotta be careful when you say it. I have no idea, you lost me.
This is control relay at the top.
Yeah.
It shows the output by the way it's drawn.
Yes.
At the top, right? So once that is connected, it's working now because you started the motor.
Well, that's
The
not a motor.
control
That's not a-
relay.
This is not a motor.
Okay.
This has no output. There's no way in the world this is a motor. This is
Then
the
how do you say that when it's energized?
You say when it's energized, or
Okay,
you say it's true. Usually a PLC, you say when it's true or energized.
But that's the first thing that
Yeah,
becomes
but this is not,
true.
this is not a motor. This is a bit file. This does not have an output, so it cannot run a motor. So this is an internal, we call this an internal relay. This is software. There's no hardware at all about it. It's B3. It's a B3. It's not an output.
Well, once it is energized by the start button.
Yeah, well,
Okay.
this has to be true. This has to be true. And then when this becomes true, this would energize or become true.
Which affects the other two that have the same address, correct?
Right. We close this one, so now I can let go of my start button and it seals in. We call this a memory circuit.
Starts that one, or rather energizes the second control relay to the same address, which in effect,
Now this
Get
is,
your
this
job.
could be, this is not a motor, but he's calling it a motor. This actually generates an output on your output port, right? And then you're gonna have a voltage there and you're gonna have a current available. And you can either hook up a very, very small motor or you can hook up
Basically, it's an output that maybe leads to a motor.
Right.
guess I'm just trying to follow the circuit a little bit and the way it's drawn, and then it rings the bell.
RS Logic for some reason didn't appear to run the program. Yes, we need to. So I'm gonna change this to a what? Yeah, I'm gonna change this to a examine if closed. Okay, and then we'll run the program. Well, I know it's going. Then we'll download it again. Anytime you make changes like that, you need to download every time, right? Now it's true because I'm using an examine if closed and the switch is what? Closed. So I come over here and press this thing when it, okay, we okay? And then I come up here and do switch 1. And notice what did it do? Let's stop it. So now I can stop it. So I'm gonna come over and hit this. Everything stops. Okay, now I'm gonna come over here. What's gonna happen? As soon as I hit the start button, it's a momentary contact push button. It's gonna energize B30. Now that's gonna close this contact right here. So now, even though I let go of the button, this is sealed in, right? You understand that? As soon as that seals in, then I come down through here, and this probably needs to be a switch. It's 1, 2. So let's change this to a switch. So on Logic Pro, to change the function, you can just hit the right one, and now it's a switch. So what I'm gonna do is I'm gonna close it and see how the job. So stop. Okay. Which has nothing to do with that. Oh my goodness.
The jog would have to be,
The jog's got to be in the ceiling. He's got it wrong.
basically the job circuit then would be opening the circuit.
Yeah. So where the jog should be at is the jog should be here. But then we have to figure out what to do there. I have to go back and look. It's okay. We're not going to correct the circuit. The circuit's got a problem because what happens as soon as I hit, if I come here and close the jog switch, it turns the motor on. Well, it will jog. Okay, so that works. So this jogs it, right? And then if I come over and hit this one, it does what? It runs, right? So the jog, it's right. The jog will run. Can you see how it seals?
Yeah, the jog will work whether or not the on switch is on or not.
Well, the switch will work, but it don't mean anything because we got it in run. So I can come down here If the motor's running, then jogging means no difference, right? See the switch actually go into play. See that? Well, that does need to be. If I stop it, then I can come down here and then we can jog the motor. But with the motor's running, jogging, you can't jog the motor with what running. But see, that's a major. So every diagram that he's drawn from then on, when he hooks it up to the PLC, he uses a normally closed stop button. But then in his program, he uses the examine with open instruction.
Doing kind of like everybody else is doing.
Right. Well, the PLC that he's playing around with probably has nothing but normally open push buttons on it anyway. So if the PLC, if the trainer you're paying with has nothing but normally open push buttons, then you've got to use that, right? You understand? But it's a trainer. It's not in real life. In real life, that button is going to be a what? It's going to be a normally closed push button. So I guarantee you that's what he did. So on this 1000, the only push button I've got is normally open. So if I wanted to program one of them as a stop button, then I'd have to use an examine if open push button, right? Unless I use a what? Yeah, unless I use a what? Yes, I simulate a stop button with a switch. So see, every one he does that, when he does his diagram, he does it, when he does his connection to the PLC, he does it right. Then when he does his program, he does it wrong. Let's look at, tell me what's wrong with figure 6-29. Mine's wrong too. I'd rewrote it. Can you see what I did? I repeated the switch. Yeah, I tweeted twice. So what I'd have to do is add another control circuit up there to control it. But what you got to understand, that control relay, this guy here would have to have an output. This guy here would have to have an output, and this guy right here would have to have an output. Those control relays, their contacts never leave the control diagram. So those could be internal relays, right? Y'all understand? So yeah, so what he's done is exactly right. I mean, he said, well, I'm going to take all these stop buttons and put it. So if you look at 125, that's great. Figure 6-30, that's great. You know, so what he's done, he's combined all his stop buttons into one stop button. He's combined all his RPB buttons into one button. He's combined all his GPB buttons into one button. And he's combined his TSW into one button, which is what we would do when we took this over. So you're talking about a lot smaller when we get into PLCs. Are we okay? And he's done the same thing over here when he did the diagram. So what has he done over here on when I look at 126, what type of button is he used for the stop button? He's using the normally closed. What does he have over here in his diagram for the circuit? An examine if. He's using an examine if open instruction. But the diagram is okay. So when he ran this, what he did is he used the normally open push button, and so he drew it like that. We'll skip over creating reports. I'll try to do one for you. Data files. Save and retrieve the program. Are y'all okay? So what do? RSLogix is going to make you save all the time. Usually every time you upload, when you upload the program, it's going to want you to save it. So what happens is you'll end up with 15 versions. Every time you upload a program, it's going to save it for you. It's going to ask you if you want to save it. Normally, every time you upload, I'm sorry, every time you download, every time you download the program, it's going to ask you for a revision number. So a lot of people, so normally, once you got the thing written, you don't download it anymore, right? You understand? So if you download it a second time, it takes for granted that you've done what? You've changed something. So a little thing will pop up there and it says, do you want to do a revision number? Normally you just pop something in there, right? You understand that? And you're going to end up with a lot of programs out there on either a hard drive or a USB stick. I wish you would put your programs on your USB drive. If you don't, then what I have to do at the end of the term is go back here and erase all these. But that's about it for this chapter. Y'all got any questions? So, upload, what do we do when we upload? So RS or Logic Pro don't give you that ability. But when I look at my true RS Logics, I got two options. I can do what? Download or upload. Now what's the difference? Download is when you take the program that's in your computer and put it into the PLC. Upload is when you take a program in a PLC and bring it down into your computer. Y'all understand that?
Download is when you take the program.
Yeah. And that got me totally confused because I dealt with the internet and networks a long time. So usually, but you got to understand both these devices consider themselves to be computers. So when I first started into PLCs, so this is their area. So to upload a program or download a program, you have to make sure that you're on the what? Online mode. Everybody okay? You switch between on and offline right here in the upper left-hand corner. Here's your main control switch right here. So I come over here, click on that. By the way, on the 1000, you switch every mode with the computer right here. If you're on the 504s, if you put it on remote, you get this same option. If you're using the key, right, you got two modes. You got program mode and you got run mode. So that means to upload or download a program, you got to put it into what? The run mode. The what? Program mode. And then to run your program, you're about to switch it to the run mode. If you put it in REM, that means remote, and you can switch it back and forth from here. Everybody understand that? Okay. So if I wanted to upload a program, we'll create programs in what? Create programs offline, right? You understand? And when we get it the way we want to, then we'll have to go what? Online. Now it does a lot of this for you. So if you come up here and you're offline and you click download, what do you think it's going to tell you? It says, do you want to go online? And you switch that, it'll switch everything for you, right? And it'll pop up, you want to do this, you do that, right? You understand? And it'll switch for you. But if you want to create a new program, then you're going to have to create the new program offline. Everybody understand that? No problem there. So if I upload, it's going to take the current program that's in the PLC. By the way, and this is what RS Logic does for you anyway. If you turn this sucker on and you hook a PLC up into it, and after it connects to it, it will automatically download, upload whatever's in the memory of the PLC at the time. So this program right here was in there. Now what you do lose when you upload a program is you lose all your symbol names, because the symbol names are not put in the PLC, right? Those are
Those are unique to the program itself. If you load a program off your disk, then you get all the simple things that you stored with. Everybody okay? If you download a program, and why I'm saying this, I got over there on the dang camera control line the other night, hooked up, not the other day, and I hooked up to the dang PLC, and guess what I chose to do? I chose to download the program. And guess what I just blew out? The program that was in there. So backups are very, very, very important. Even I make mistakes. Let's sit down. Even I did lecture. This is the program running right now, by the way. It's been running the whole time. I'll look it up. This is the program that takes a motor, runs it forward for so long, it'll stop, it'll let the motor come coast to a stop, and then it'll reverse, and we'll sit there and just run all day long. Lunchtime, where we're going to meet after lunch?
In the lab.
In the lab, yeah.